Good afternoon and welcome to the second of the Ian Ramsey Centre Seminars for Science and Religion for Hillary Term 2018. The title of today's talk is Astrobiology, Searching for Life Beyond the Earth. And we're very pleased indeed to have Professor Rafael Vicuna here to join us all the way from Chile. Just arrived, I think, yesterday. There's a new British Airways direct flight from Chile. I'm very pleased about that. And I'll give the formal introduction and then I'll make a few informal comments. Professor Vicuna is a member of the Chilean Academy of Sciences, the Latin American Academy of Sciences, the World Academy of Sciences, the Pontifical Academy of Sciences, and the Pontifical Council of Culture. He's the author of more than 100 publications in the fields of enzymology and gene expression in bacteria and fungi, as well as about 50 publications dealing with science and society and science and religion. He obtained his PhD in molecular biology at the Albert Einstein College of Medicine in New York in 1978. He then joined the Faculty of Biological Sciences at the Pontifical Catholic University of Chile, where he's been a full professor since 1994. In 1996, he was awarded a Guggenheim Fellowship. During 1997 to 1999, he served as president of the Chilean Society of Biochemistry and Molecular Biology. He's also former Dean of Research and Vice President for Academic Affairs at his university. His research has included work on life in the Atacama Desert in northern Chile, which is the driest and oldest desert on Earth, and has proved an excellent terrestrial analog site for Mars. So we can't easily go to Mars, but we can look at northern Chile and have some intelligent guesses about what life might be like under these extreme conditions. I'll make a few informal comments as well. I'm just, one of the great privileges of the last several years working on a project in Latin America has been to meet Professor Vicuna. It's a Chilean gentleman, very polymathic individual in his range of interests, literary and humanistic as well as scientific, and has been an enormous help with us in our Latin America project. We've reached several hundred promising young scholars, given them opportunities, but always we've been able to consult Professor Vicuna, and that's been an enormous help to us and a great privilege. And the last and final big conference of the project was held at his university just last September, and we had a stellar range of speakers, including an astronaut from a Mexican background and all kinds of other interesting figures, and it really was a stunning end to a wonderful project. So it's with great personal pleasure and gratitude I'm happy to welcome Professor Vicuna here to talk on astrobiology, searching for life beyond the Earth. Thank you.
Good evening, everyone. Thank you very much, Father Andrew Vincent, for your very kind introduction. It's a big pleasure for me to be here once again. I gave a seminar at the Ian Ramsey Center 3 or 4 years ago, and in that occasion I spoke about the microbiology in the Atacama Desert, and we had some discussions on the origin of life as well. And today, well, I will be talking, as it has been announced, on astrobiology, or searching for life beyond the Earth. I am also very pleased to be visiting Oxford once again. This time I am participating in 2 activities. One is this seminar, and there is also a symposium on Thomas Aquinas and modern biology at the Blackfriars College on Saturday. So that will keep me busy for these 4 or 5 days that I will be in Oxford this time. And I enjoy the weather, of course, because it's hot summer in Chile this time. Well, as you may know, well, let's see, I have this device here now. Astrobiology aims to understanding of the origin, the evolution, and distribution of life in the universe. And this is a question that humankind has been asking forever, okay? Are we alone in the universe? Is there any type of life elsewhere? And when you come to think about the possible answers to this question, I see at least 2 alternatives. Either there is life only on Earth, or there is life everywhere. And by everywhere, I mean millions of places. And we can safely say that now that we know that there are millions of planets like the Earth, planets that we would call habitable for the type of life that we know of. And either response, either life only on Earth or life everywhere, I think it's thrilling, it's electrifying. And of course, in either case, we're invited to reflect about life, especially about human life. Now, the easiest way to find out about life beyond the Earth would be to, for example, send manned missions to other planets or moons, or to send spaceships to bring back samples to Earth to be analyzed for the presence of biosignatures or microorganisms. But up to date, our technology doesn't allow that. So astrobiologists are following a series of approaches that are indirect to detect indirect signs of life. One of them is studies of life in extreme environments on Earth. And what we are aiming at in this case is to look for life or to study life in environments that mimic in some way the environmental conditions of other planets or other moons in our solar system or other solar systems as well. And we have learned how flexible life is to adapt to very extreme environmental conditions. Another option is, or approach is to inspect planets or moons in our solar system, sending spaceships, remotely also detection of biosignatures, studying the atmosphere of those bodies. We will be talking about that later. A third approach is search for exoplanets that started about 2 decades ago, and it has been very successful. We know now that there are many billions and trillions of planets in the universe, and just due to statistical reasons, there should be millions of planets that have conditions for the development of life as it took place on Earth. And for the moment, we can hope that we could remotely measure some signs of life in those planets because they are too far away. And then there is a project that has been going on for about 50 years now, which is the Search for Extraterrestrial Intelligence, SETI. Most of you, I'm sure, are familiar with this program, and I will be saying a few words about it. Let's see, about life in extreme environments. We are so used to see all forms of life around us, plants, animals, and so on, and we tend to forget that most of life on Earth is microbial. We don't see it, but the great majority, the great diversity of life on Earth is microbial. And microbes develop not only and proliferate or thrive not only in what we would call friendly environments, but as I mentioned before, microbes very easily adapt to changing environmental conditions. And some of them are pretty extreme, and we call these organisms thriving in these extreme environments extremophiles. So we have acidophiles living at very high or low pH, thermophiles at high temperatures, alkalophiles at high pH, psychrophiles at low temperature, xerophiles in environments lacking liquid water, halophiles high salt, barophiles in the ocean floor, for example. So we see organisms in all these types of environments. Let me show you some few examples, because this is very, very impressive. And I take this table from the Brock textbook, I think one of the most prestigious textbooks in microbiology. This is the 14th edition. Some examples of extremophiles. For example, the thermophile is an archaea that grows at optimal temperature of 106 degrees. And the lowest temperature is 90 degrees. And of course, the water there at 106 degrees is not boiling, because this organism lives in the ocean floor, in the hydrothermal vents in the ocean floor. And the maximum is 122 degrees Celsius, okay? Always in liquid water. And the opposite, a psychrophile, in this case a bacteria that grows in small droplets of liquid water inside the ice, at the optimal temperature is 5 degrees. The minimum temperature is -12. So that this bacterium would be fine growing today in Oxford, for example. Okay, Then with respect to pH, at a low pH, at less than 1, okay, a value of less than 1 or above 10, a very alkaline pH. This is another bacteria, and in this case, an archaea. There we have many examples of organisms growing at very high pressures, like 700 atmosphere, or on solutions saturated with salts. So when we see life proliferating under these conditions, we tend to believe that even though some environmental conditions of certain planets or moons do not look too very friendly to us as we would like them to look, we can hope that there will be life even at high temperatures, high pressures, and so on. We have so much to learn, and there are so many interesting examples of extremophiles. And I am pretty much impressed with this case, for example. This is a report published by a Japanese group 2 years ago. They drill a hole 2.5 kilometers beneath the seafloor, okay, in some ocean near Japan. So, and there is a layer of coal there, and they found microorganisms producing methane there. So we're talking about 2.5 kilometers starting from the bottom of the ocean. I think it's the deepest hole that has ever been drilled for looking for organisms. So you have a community of organisms growing there, developing there, completely isolated from the rest of the biosphere in a very unfriendly ecosystem. They don't depend on the sun. They don't depend on organic matter provided by other organisms. They make their own organic matter, fixing CO2 through inorganic reactions. And the most interesting life on Earth is chemioautotrophic, as this bacteria. So you see, you would never have dreamed that there would be life so deep in the Earth. Okay, so other possible habitats in our solar system that are suitable for life as we know it, this has been said so many times that we know only one kind of life. There could perfectly be other types of lives, and that would take us to discuss what life is, and we would never end this seminar. So if we are talking about finding life elsewhere, I will be referring the type of life that we know here on Earth, which is only one type of life. It's the same molecular logic for all type of life that we know of. And astrobiologists have developed the concept of the habitable zone for a solar system. And this has basically to do with the distance of a planet from its star that would allow the water to be liquid. Okay? So if we see a scheme of our own solar system, this would be the sun. Here we have the planets. Only the Earth would be in the habitable zone, and perhaps Mars will be in the boundary of it. And of course, the habitable zone will be related to the energy of the star, because if it is a big star radiating lots of energy, the habitable zone will be far from it. If it is a small star radiating less energy, the habitable zone will be closer to it. And in the case of the Earth, we know now that there may be other places in our solar system that may have liquid water, because the physical state of water will not depend only on the energy provided by the light of the sun, the solar energy, but also in other phenomena like volcanism or tidal forces, for example. So what places in our solar system have been considered as possible environments for life? Well, we have to keep in mind the moons. We always think on planets, but we have to think on the moons also. And I will be showing you moons. In this case, I am showing 4 moons of planet Jupiter, the 4 Galilean moons, and one of them is a very good candidate. It's called Europa. Europa is similar in size to our moon. It has a metallic core in the center that is surrounded, covered by a rocky material. And at the surface, it has a layer of water, of H2O at least, okay? And we believe it is liquid, but of course on top, the crust is ice because of the temperature. It's too far from the sun. But due to tidal forces and perhaps to volcanism, astronomers believe that there is liquid water. So we have here a moon with a solid core, of course, but all the rest is water. NASA is exploring through different means Europa, and they approved a couple of years ago a budget to construct some robots that will go to Europa and perhaps drill the surface and explore, the ocean, looking for signs of life. 2 years ago, the NASA's Hubble spotted some possible water plumes in Europa, if this is confirmed, it will be much easier to sample the ocean from Europa because we will not have to drill the surface. So this is a good candidate, Europa, and there have been movies and science fiction movies. It is so difficult to imagine, at least for a microbiologist like myself, that there is such a large body of liquid water floating in space with no bacteria in it. This doesn't happen on Earth. It is very difficult to find a sterile place on Earth. There are no sterile places. Even volcanoes, you find life everywhere. So you see a big ocean with no microorganisms in it is very difficult to conceive for a microbiologist. So I think there is life there. Now, every time we analyze foreign environments, we're thinking on Earth models of those environments. And Europa has some, and perhaps the best one is Lake Vostok in Antarctica. This is the largest lake of course, liquid water beneath ice. Okay, so this is in Antarctica again. It's covered by 2.2 miles of ice. And the big challenge here is to sample that water to see if there are microorganisms there. And why do I say it's a challenge? Not to drill. Well, it is already a challenge to drill 2.5 miles into the ice, but you have to do it under sterile conditions. You have to make sure that you're not contaminating the water in the bottom. So they started to drill this hole in 1990, and they have stopped several times, and they stopped completely when they reached what is called the accretion ice, the limit, the boundary between liquid water and frozen water. And they have taken samples from this accretion ice. They are always fearing that if they touch the water with the probe, they may contaminate the water, and they want to make sure, as I said, that they don't do so. For the moment, they are taking samples from the accretion ice. And this paper that was published, 2 years ago in the Journal from the Royal Society, it says this: the only phylotype passing all possible controls of contamination proved to be either to an unknown type of bacterium. Okay, there are bacteria. There are plenty of bacteria there, but you have to do some tests to make sure that they are not contaminants. And there are genetic tests to do that, and what this publication is reporting is that they found a new organism. And most likely, if it is in that accretion ice, it is also in the water beneath it. We will have to wait for future experiments in this Vostok Lake. But I know of this publication only reporting microbial life there. But it would be surprising, for at least for us microbiologists, if that lake is sterile. And again, if they find and they confirm that there is life, it would mean another environment that is completely isolated from the rest of the biosphere. And they are getting their own energy and organic compounds and so on, and they manage to survive there. Another possible site in our solar system is a moon from Saturn. This time is Titan. I am showing some of the moons. Either Saturn or Jupiter, they have more than 60 moons each. So I am showing a few moons from Saturn, among them Titan and Enceladus. Enceladus is the one I think that you use for the poster for this seminar. Okay, Titan first is about 50% bigger than our moon. It is cold, of course, minus 180 degrees Celsius. It has an icy surface with lakes of hydrocarbons. There are lakes of methane and ethane, and it rains hydrocarbons there in Titan. Scientists are hoping that there will be liquid water beneath the ice due to volcanic activity, but that has not been confirmed at all. The atmosphere is mainly nitrogen, and Titan was the second moon in which humankind landed. That was 2004. So since 2004, there is a spaceship on the surface of Titan, and it was taken there by the Cassini orbiter. The Cassini took photos of the lakes of hydrocarbons, and this is a photo taken by Huygens lander. It impresses me very much to see, the surface of a moon, of a faraway moon. And since we are talking about Cassini, I'm sure you read this in the press a few months ago, because after a successful mission of 20 years, Cassini was orbiting Titan, and it was directed to take a plunge in Saturn. That was September 11 was the last, it was called to come to Saturn on September 11. On September 14th, it took the last image, and then the last signal was sent on September 15, and then it disappeared in the gas of Saturn. One of the main concerns of astronomers and astrobiologists is not to contaminate other worlds with Earth bacteria. So the Cassini, after 20 years, may have carried some microorganisms. And I think that the reason to make it to plunge into Saturn was to make sure that it would not contaminate, Cassini would not contaminate other bodies in the solar system. Okay, other environmental analogs to Titan on Earth, yes, there are some. This is Pitch Lake in Trinidad and Tobago. This is a lake formed out of asphalt and petroleum derivatives that are emerged from to the surface. And there have been some microbiological studies conducted in samples taken from this lake. This was published, for example, in the journal Astrobiology a few years ago. And the bottom line is there is plenty of microorganisms proliferating in the asphalt, in this organic material. And they have the same biochemistry. The only difference is that they have the ability to degrade, to metabolize some organic compounds that normally are not metabolized by other bacteria. But this is not a different kind of life, you see. So in Titan, we could have life as on Earth growing on the hydrocarbons of Titan, but using Earth biochemistry, you see, because it would be basically the same metabolic pathways based on water and carbon and so on. There is another analog. It's a Rancho La Brea in California, also filled with life. No matter where you take samples from in Rancho La Brea, look at the type of material. It's asphalt and petroleum, and it's loaded with microorganisms. Okay. And then a third moon in our solar system, Enceladus, also from Saturn. This photo was taken by the Cassini. It's 8 times smaller than our moon. It presents numerous grooves and fractures in its icy surface, suggesting tectonic activity. But for some time, various shapes in the relief of the surface suggested water exits from a possible internal ocean, and this has been confirmed now. Cassini, and this is for sure much better evidence than from Europa, has observed plumes of water coming off Cassini, which is coming off Enceladus, so which is very indicative of some volcanism taking place in the rocky part of or in the bottom of the. I haven't said that it is expected that Enceladus, of course, has a rocky interior, a core, but surrounded by an ocean, and that's why we see these water plumes. But to me, the most important finding, recent finding in astrobiology is this one. It's the report by a group in Science last year of the presence of hydrogen in these water plumes. And hydrogen, we know how it is produced on Earth by the process of serpentinization. And the reduction of CO2 by hydrogen in hydrothermal vents is one of the main theories for the origin of life today. So having a molecular hydrogen coming off in these water plumes is very indicative that there is some hydrothermal activity taking place in Enceladus. And nobody has proven, because it's difficult to prove, that life started in hydrothermal vents. At least, in my opinion, it is the best theory that we have. So it is very intriguing to have this ocean, to have liquid water, and to have hydrogen there that most likely is being produced by a hydrothermal process. We'll have to wait for more data. But Cassini is not there anymore, unfortunately. Okay, then we have planet Mars. We have it here in scale with the Earth. It's much smaller than the Earth and the Moon. And these are the conditions: a very low temperature, surface temperature, and the average is about minus 70 degrees Celsius. A very low atmospheric pressure. It's mainly composed of CO2. Very low humidity. We think that there is no liquid water on Mars, at least on the surface. We know for sure that there is ice. And there is high UV radiation because the atmosphere is too low. This is a diagram of the Discovery rover that is, as we speak now, is exploring Mars. There have been many rovers exploring Mars. They started in 1976 with the Vikings. I remember that I was a graduate student in New York when the Vikings sent the first photos of the surface of Mars. Very, very impressive. And this is the only mission that has carried out experiments to measure metabolic activity. And the results obtained in those experiments were not conclusive. And for some reason that I ignore, people is not discussing them anymore. But I will go back to that. Okay, so these rovers are equipped, these are robots equipped with all sorts of fancy instruments. After the Viking, we had Pathfinder, then the Spirit and Opportunity, then the Phoenix in 2008, the rover in Curiosity 2012, which is the one I am showing here, and there will be another rover launched in 2020. And as I was waiting for the bus yesterday in Heathrow to come to Oxford, I read a Chilean newspaper. The main Chilean newspaper is called El Mercurio. Here is the date of publication yesterday. They had in the front page the experiments conducted by NASA, because NASA has laboratories in the Atacama Desert in northern Chile. They test all the instruments and the robot there. And this rover that they will launch on 2020, they are testing it today in the Atacama Desert. You see? It's a big, interesting coincidence. Well, the Curiosity rover has, as I said, only the Viking mission looked for signs of life. All the rest of the rovers have looked for, water, of course, liquid water, and they have done some geological studies, but they have not looked for signs of life. But they still do some measurements. For example, the Discovery has found long-chain organic compounds, some oxidized forms of nitrogen, gas methane, and methane had been detected remotely in the surface of Mars. And there has always been an argument about this because it comes and goes. And we know on Earth of only two types of producing methane: volcanic activity and metabolism. The methanogens produce methane. So since we don't know of active volcanoes in Mars today, most likely if we see methane, it could be that there are microbes producing it. And as I said, there was a big argument about how real were those determinations, and now Curiosity has confirmed that there are some levels of Mars in the atmosphere of methane in the atmosphere of Mars, and there has been some reports on liquid water, but again, there is no consensus about it. I wanted to show you this publication by Gilbert Levin and Patricia Anstrat. Levin is the one who designed the experiments in the Viking back in the 70s. And he recently published this paper in Astrobiology 2 years ago, reivindicating his experiments, and he's wondering why the scientific community is not paying attention to the results obtained in these experiments, because I know for sure that they were not conclusive, but they did not rule out the presence of life there. So perhaps more information can be obtained with the same data. And so what he's doing in this particular paper is trying to convince or motivate the scientific community to go over those results again. And he says, these are the only experiments that we know for sure we will ever do that will not be contaminated by life from Earth. Because there may be many microbes on Mars now, but taken by the rovers, you see. But these were the very first experiments. These are the only experiments that we can tell for sure that were not contaminated with Earth microorganisms. I tend to sympathize with Levin. This is very quick. It was published last month. Only to remind you that Mars Reconnaissance Orbiter, this is a remote discovery, found cliffs, underground ice cliffs. There are, a huge amount of ice, frozen ice, and this may be interesting for future manned missions. We will not have to worry about where to get water from, because there is so much ice in Mars. Okay, what are the Earth analogs of Mars? There are two, the dry valleys in Antarctica and the Atacama Desert, as we have mentioned before, in northern Chile. The dry valleys are very cold. The temperature ranges between -50 in winter to +2 in summer, and they are called the dry valleys because there is no liquid water there. The water is either ice or there is no water. It sublimates to water vapor. So the air humidity is very low, about 10%, high UV radiation, just like Mars, high salt salinity, exactly as Mars, and very low levels of nutrients, like Mars. There have been some microbiology studies conducted in samples from the dry valleys, and of course, as you would expect, there are tons of microorganisms, but they look for niches where they will be protected from the radiation, from UV radiation. So they grow inside the stones, inside porous stones, and those communities are called endolitic. They grow below quark transparent stones, and they are called epolytic, and they can do photosynthesis with the light that is transmitted after it crosses the transparent stone, which is not too much, but enough to carry out photosynthesis and to feed other microorganisms with the products of photosynthesis. This is a typical rock you see, where you see the line of chlorophyll of cyanobacteria. These are samples from the Antarctica. And with respect to the Atacama Desert, it certainly looks like Mars, at least to your side. This is a photo taken by one of my former students, and we can transform the Atacama Desert into Mars with just touching one bottom, you see, there. And the conditions were, as Father Andrew Princeton mentioned before, is the driest and probably oldest desert on Earth. It has very low humidity and almost complete absence of rains. There are several places in the Atacama Desert where there are no recordings of rains. High solar radiation, very high. Highly saline soils with nitrates, chlorates, sulfates, and so on. And soils in the hyperarid region possess two Mars-like properties: low levels of organics and non-specific chemical oxidants. There was a famous paper published in 2003 in Science with the title "The Atacama Soils or Mars," with a title similar to this. I don't remember exactly, but they are reporting that the soils in Mars are very similar to the soils in Atacama with all these parameters. When I was a student, I remember to have been taught my professor at the university that the only place on Earth where there is no life whatsoever is the Atacama Desert. And I had tried to look for a printed statement saying that. I have not been able to do so. I have looked in books and papers and so on. But I found this interview made to a very prestigious astrobiologist, Chris McKay. He was interviewed in 2004 about extremophiles. Okay? And you can read by yourself. Specialized microorganisms called extremophiles thrive in nuclear waste, volcanic vents, boiling geothermal geysers, and even deep inside rocks. Their unique biology allows them to feast on chemicals and radiation that would kill most organisms. I underline this now. But there is a place on Earth so hostile that life at even extremophiles perish, the Atacama Desert in Chile. And this is quoting now Chris McKay. Here is the only place where we have really crossed a threshold where we find no life. That's what I was taught a few years ago. No, many years ago. Okay, but we were not looking right in niches where life hides to protect against solar radiation. I wrote a review some years ago on the microbiology of the Atacama Desert, and we know now there are millions of different types of organisms growing again inside rocks, inside salt rocks, the halides. And when you break a rock made of salt, you also see a boundary of chlorophyll. As the salt attracts water, the bacteria know how to get the water from the grain salts. Then in caves, for example, and underneath the ground, below the soil, if you, for example, seed microorganisms on the surface of the Atacama Desert, they will die in hours because of the solar radiation. And that's what people was doing before. They were looking in the surface soil, and they couldn't find any. But you have to dig a hole, and you will see a zoo of microorganisms. So this is some of our work. We did a collaboration with Chris McKay after a few years after he gave that interview, and we published this in Microbial Ecology. There are few patches of quark stones in the Atacama Desert. So you lift a stone, and underneath you see the chlorophyll of the community, mainly cyanobacteria, growing with a photosynthesis that is allowed by the transparent rock. And there are many more microorganisms that are supported by the what we call primary producers, the bacteria that are able to conduct photosynthesis. It doesn't rain here, but there is fog coming often from the other side of the mountain, and these organisms have developed ways, biochemical tools, to trap the water underneath the stone. The main component of this community is cyanobacterium Gleocapsopsis, and we have a test to see survival of bacteria after we desiccate them. So we add a hygroscopic substance, and we form a film of completely dried bacteria. And we have a test to distinguish between viable and dead bacteria, and we can desiccate cells for several days, for months, and after 2 years, about 70% of the cells that have been desiccated, completely desiccated, it's like a cellophane film that you can see through it, made of bacteria. Then you add water 2 years later, and about 70% of them have tolerated the dryness. And then I like this publication very much because, for many years, NASA has been working in the Atacama Desert in a place called Yungay. And there are historical reasons for that, and there are logistic reasons for that, but they never conducted any thorough study to see what would be the driest place in the desert. And we did so. We bought these tiny sensors, and we distributed sensors in the Atacama Desert. We could leave them there. Nobody would come and steal them because it's a very hostile environment. And we came back 6 months later, and of course these sensors record everything. You plug them into your computer, and you have daily recordings of temperature, humidity, and so on. So we described what we believe is the driest place on Earth. And we dug a hole. Of course, there is no life on the surface. We dug a 1 meter hole, and then every 20 centimeters we took samples, and we found millions of microorganisms, most of them pigmented. And you would expect that for organisms that are, at least they have the possibility of receiving some sunlight, because of course a pigment would protect them from the formation of free radicals and so on. But, well, okay, there are tons of microorganisms there. So we sent this for publication, saying that the life in the driest place on Earth. And the editor said, okay, you know, I like your publications, but you cannot say that this is for sure the driest place on Earth. So you change the title and say the driest place in the Atacama Desert. And we had to do that. But again, we are proving here that you don't need the Caribbean to have life, okay? You can have, well, there is life everywhere. And before we moved into the exoplanet chapter, we don't only are exploring moons and planets, but also comets. And this is the Churyumov-Gerasimenko comet. In 2004, the European Space Agency sent this Rosetta orbiter with a Philae lander, which landed onto the comet. 10 years later, you have the dimensions of the comet and the weight, the size and everything. And this lander was equipped with a mass spectrophotometer. And it didn't surprise me to learn that they found, these Philae instruments, among them the spectrophotometer, found many organic molecules that could be related to life. But you know, the comets that come to Earth once in a while are loaded with organic compounds. And it was the case also of this Russian named comet. Well, again, it amazes me that we can send a lander to a comet that is moving. It has an orbit of 6.5 years around the sun. This is just men's curiosity. I like it. Okay, now let's move to the search for life beyond our exoplanet. This is a big program now, and both ground-based telescopes and space telescopes are being used. Many ground telescopes, but most of the planets, or exoplanets, of course, are detected with the space telescopes. You have the names here and the launching data, the years, and there is one that is going to be launched soon, the TESS. These are NASA, these are European. So there is a big effort now to find exoplanets. And there are two methods to detect an exoplanet, and this is not my field, but I think I understand the basics. This is the problem with astrobiology. If the lecture is given by an astronomer, he will have to guess most of the concepts in biochemistry and microbiology. This is an interdisciplinary, of course, task, so we have to help each other. But this is simple. So there are two methods to detect, main method to detect exoplanets. One is the transit method. This is so difficult to believe, but it is actually how they do it. So when you have a planet orbiting a star, when the planet is between the observer, for example, the space telescope, and the star, it dims the light a little bit. And this is periodical, you see? And what I find so amazing is the sensitivity of the instruments, because stars are big and the planets are very small. But here, for example, for an Earth-sized planet, the dimming is about 0.01%. And a change in this range is in the sensitivity of the Kepler telescope, for example. It's amazing. You have seen drawings of the sun next to the Earth, and you would never believe that the Earth would produce a detectable dimming of the radiation of the sun, but it does. And this is how most of the planets have been discovered. And the other method is a radial velocity method, and again, this is very impressive. The planet is orbiting the star when the planet is between the telescope and the star. It pulls the star towards the telescope because of its gravity, and when it is away, of the telescope, or behind the star, it pulls a star away from the telescope. A tiny planet pulls a big star away. But again, it is detectable through the spectra of the light emitted by the star, because when it is receding, it will move to the red. It will do a redshift, and when it is approaching, a star approaching to the telescope, it will be detected by the instruments. Very impressive. Okay, there. What am I doing? Okay, this. You can follow what is the state of the art in terms of finding new planets, because there are several sites in the internet. This is the one that I see most often, the NASA Exoplanet Archive. This is the last edition of it. So there have been almost 4,000 exoplanets completely confirmed. There are many more candidates. I have learned that several groups have to agree on the data to confirm that there is a new exoplanet. They can be classified in terms of the method that it has been used. Most of them, transit and radial velocity. There is direct observation for a few, and some other sophisticated methods. And you can classify them by size. For example, the radius will be related to the dimming in the transit method. You don't know about the consistency of the planet in the transit method, but you see the size. And as opposed to that, in the radial velocity method, of course, the pulling of the star will be a function of the mass of the planet. So you have the radius, you have the mass, and you can calculate the density, and you can figure whether it is rocky or gaseous, etc. So this is the radius with respect to the Earth, and this is the mass with respect to the Earth. There are all types of classifications. And so what astronomers are doing is they are listing them as according to their potentially habitability. They have devised a method called Earth Similarity Index. They list the properties of the Earth, and they see to what extent these planets fulfill the conditions of the Earth. So you have, of course, the Earth Similarity Index for the Earth itself is 1. And you see some planets here, Proxima Centauri B, Trappist 1e, etc., are similar to Earth in size. Here you have the actual sizes of the Earth as compared to Jupiter and to Mars, to Neptune. So these are pretty much the size of the Earth. And they are all in the habitable region. They are all rocky. So you would expect that there will be liquid water. There is water everywhere in space. So you would expect that there will be liquid water in these rocky planets. It's coming to come similar, is starting to become similar to Earth. And here you have one of the latest statistics. I couldn't find a new one. I think this is the last one they have published. About 50 planets that are very similar to Earth. Some of them are bigger than the Earth. So we have many candidates now. And just to show a few examples, just to remind you that there are all types of stars. So you have the Sun here and the Earth to scale. And you have this Gliese 1132 star with a planet similar to the Earth. So the orbit is much closer to this star with respect to the Earth and the Sun. This is an interesting system called the Trappist System, which is very small. This is the actual size to scale, of course, of our solar system. So all this solar system, the TRAPPIST-1 system, fits inside, almost the size of the Sun, you see. And of course, the star is much smaller, 2,000 fainter than our Sun. And what is interesting about the TRAPPIST system, which is, I think, 40 light years away from Earth, is that it has 3 planets, 3 rocky planets, the size of the Earth in the habitable zone. What else? The closest exoplanet is Proxima. What is the name of the planet? I'm confused. Proxima Centauri is the star, and the planet is Proxima b. Okay, and this is, of course, Proxima Centauri is in a system with Alpha Centauri A and B. And what is interesting is this planet, which has a size very similar to Earth, is at let's see, the distance is about 4.2 light years from Earth. It has a 200 kilometers deep ocean of liquid water, and it is in the habitable zone, of course, and it's the closest planet to Earth in a different solar system. Interesting. Okay, and you may have seen this. This was published, I can say yesterday, in February last month. And this is very technical. I couldn't understand my astronomer friends when I asked them the technical stuff, but I will transmit you my ignorance, okay? There is something that we can consider simple. If you have an energy-emitting body far from Earth, and in between you have a galaxy, for example, you can detect the bending of the energy. That was predicted by Einstein, and that we know. It has been done experimentally. Okay, using that microlensing method, an quasar that is located, I think is, I don't have it here. A quasar that is far away, I would say 12 billion light years away, and a galaxy that is only 6.5 billion light years away, when the energy from the quasar passes by the galaxy, it forms 4 images of the bending. And you can figure the mass of that galaxy based on the bending. That I can understand. But what it follows is that based on very technical determinations, you can figure whether this bending is due to black holes, is due to dark matter, or to planets. I couldn't understand why you can distinguish that, but you can, and I believe my friends, okay? And what they say, look, this is so impressive. For some reason that I can neither understand, you can distinguish between free-floating planets and planets orbiting stars. And what this group is reporting in the Astrophysical Journal a few weeks ago is that they can explain the bending of the energy of this faraway quasar only if you have about 2,000 objects ranging from Moon to Jupiter mass per main sequence star, per star in the galaxy. Each star has 2,000 bodies, not orbiting, but free-floating planets. We are not used to this concept. I have heard astronomers speaking of Pierre Lenat, for example, in the Pontifical Academy, gave a talk a few years ago, and I asked him, how? I never heard before that there are free-floating. Of course there are. He said, of course there are, but very few. Well, it doesn't seem so anymore. So it is a new idea now, the free-floating planets. Free-floating planets, this is published by NASA, may be more common than stars. There may be much, of course, in this galaxy, they found 2,000 planets per star. So we have said before, and I started saying that there are million planets like Earth. There could very well be trillions of planets like Earth. Now, what would be the habitable zone of these planets that are floating around? I don't know. So we need to introduce new concepts, because we are so used to model, the possibilities of life on planets that are orbiting a star that are receiving a more or less constant amount of energy. But what would be the case in planets that are lost in space, that are not attached to any star? What type of energy are they receiving? This is new. This is new. I mean, it is not as a concept, but the amount of free-floating planets is something new. This is, as reporters say when in the news at night, how do they say it in English? These are news under developing. How do you say? This is breaking news is when you have something very important and you tell it. But when news are developing, we have an expression in Spanish that is very commonly said now. Okay, this is under development, so we will keep you informed. I think I could use that expression for this new concept of free-floating planets that seem to be very, very abundant. Okay, I'm coming to the end of my presentation. Okay, I cannot skip this, sorry. No, you know what? We keep saying we keep saying that the habitable zone is critical because the water is liquid and so on. But it is, I mean, liquid water is not the only requirement for the development of life. And let me say a few words about three other components that are very seldom mentioned. One is the importance of the moon. And I have written this to make it quickly. 4 billion years ago, life has started already 4 billion years ago, the moon orbited much closer to the Earth than it does now. After the collision of this planet Theia against the Earth forming the moon, it bounced and formed the moon, okay? So the Earth began to move faster, to rotate faster, so producing tides that caused periodic cycles of humidity and dryness that could have driven the interaction among the early biomolecules. There are books written on the importance of the moon for the origin of life. But not only for that reason, because also the moon stabilizes the tilt of the Earth's spin axis with respect to the ecliptic plane, giving moderate seasons and preventing temperature extreme anywhere on the planet. So it stabilizes the climate, the moon. Okay, so there you have a requirement. So if we are right in our hypothesis that the moon was important, we would require then in a foreign planet to have a moon to stabilize the environment of that planet. What else? The magnetosphere of the Earth. You know, we have a core of iron, and that creates a magnetosphere that deviates all the radiation from the sun, the cosmic energy and the high energy protons and electrons, the solar wind. It sounds very, very reasonable, at least to me, that if we are protected against ionizing agents, that would make life easier to develop on Earth. So the question is a magnetosphere a strict requirement for the development of life? We don't know, but we have to keep this in mind. And then volcanic activity. So this is something very special about Earth. The Earth layers are moving, and one of them are going beneath the other layers, and we have volcanic activity, and these tons of carbonate that are buried in the mantle, billions of years later erupt as CO2. So this is a greenhouse effect that stabilizes the temperature. And you see the title of this article, for example, that published in Scientific America, is Earth's tectonic activity may be crucial for life and rare in our galaxy. So you may have a very Earth-like planet, but perhaps if it doesn't have a moon, if it doesn't have a magnetosphere, if it doesn't have tectonic activity, it may never develop life. Okay, there is no way with our present technology that we will visit exoplanets. So how can we do it? Okay, we spoke before about the transit, the dimming of the light produced by the transit of the planet, but there is another effect produced by the transit of the planet, which is the reflection of the light of the atmosphere of the planet. And that reflection will depend on the composition of the atmosphere. I will say it in very few words. So if you measure complete light, you just see the dimming. But if you select wavelength to do the spectra, you will see the passing of the planet under certain wavelength will produce a change in the spectrum that will disappear during the secondary eclipse, when the planet goes behind the star. It will disappear, and it will come again in front. You follow that? So based on the effect, on the reflection of the light that is, or the absorption at certain wavelengths that is produced by the planet's atmosphere, you can guess what the components of the atmosphere are. And if you were to model something like the Earth, for example, you would say, okay, if I have oxygen and methane at the same time, as it is the case on the Earth, there is a disequilibrium there. Because if there is no life, the oxygen will oxidize methane, and there will be no methane. unless it is constantly produced, but then you need a source to be constantly producing oxygen, as it is in the case of the Earth. So you would look like to a disequilibrium like that, a reduced gas with an oxidized gas. This is not simple. To my knowledge, this is not being done yet, to measure the composition of the atmosphere through remote means. But it is technically possible. It will be technically possible soon. No question about that. So scientists are proposing gases that may serve as biosignatures because we have to agree on criteria, you see, to see, okay, what I am looking for? What do I expect to see if there is this equilibrium and so on? But not only composition of the atmosphere, and this is also not possible now, and perhaps it will never be, but to measure the reflection of on the surface of the planet. That if you do that theoretically and you do that to Earth from a nearby place to Earth, you can figure that there is chlorophyll on certain places of the Earth. So these planets that are so far away may also contain some pigments that are related to life. There are so many here, not only chlorophyll, carotenes, and so on, hundreds. So this Lynn Rothschild, which is a very prestigious astrobiologist, she's proposing a list of pigments that are important on Earth that perhaps will never be detected from space because they are in the water, under the water or under the Earth or whatever. But we have to keep in mind, we don't have to look for chlorophyll only. But again, this is much more technically demanding than measuring the atmosphere. But this will be perhaps possible in the future. Okay, I think, this is just to keep in mind the moons. We keep talking about exoplanets. I want to mention that we have to keep in mind the moons also. I will skip the search for extraterrestrial intelligence. There are funds now. I will say just a couple of sentences. There have been efforts for 50 years, I think, to detect signals from other civilizations, and they have been unsuccessful. And I think it's fine to do this. We have to do it. We have to do it. The problem is how to finance it. And the SETI program, the SETI Institute, has had some problems getting support for these measurements. And the SETI Institute is mainly financed now by donations of the general public. And they do some research. They have education programs, they have programs, and they have outreach programs also. But what is interesting is this foundation funded by a Russian millionaire, Yuri Milner, who founded Breakthrough Listen Initiative. And he's donating $100 million for the search for extraterrestrial intelligence. He signed an agreement with the Berkeley SETI program, and there are telescopes in the northern and southern hemisphere looking for signals coming from the space. So there is people willing to invest in this project, and I'd like to hear that. This initiative was launched in the Royal Society in London. You can see Stephen Hawking here, Martin Rees, Frank Drake. Frank Drake, that name may sound familiar to you, is the one who made the equation, the Drake equation, to see what are the likeliness of life of civilizations in other places. So there are efforts there are still efforts and several telescopes. And again, in El Mercurio, sorry, I am glad to tell you that the Chilean press has improved in terms of informing about scientific events and activities. So this was also published in Mercurio in February last year, 1 year ago. New telescopes are joining the Yuri's Breakthrough Listen initiative. And I like that. I had the opportunity once to have dinner with Frank Drake some years ago. And I asked him, okay, tell me, did you ever listen to any weird signal from outer space? And he said, the only signal that we hope to be foreign, from a foreign civilization, turned out to be a washing machine in Japan, for example. But no, we have to keep looking. This is the last. Just to remind us that we have to think what is the likeliness that there may be other types of life. we have to think on that. We know only one type of life, and when we look for life elsewhere, the question is, what are we looking for? It is going to be like the Earth? Well, so we have to reflect, and this is a report issued by the National Research Council in the US. You know, it's the Academy of Sciences, of Medicine and Engineering, that they join forces in several programs, and in this case to speculate on possibilities of life based on other chemicals. You can see I selected two of the chapters here: alternatives to Terran biochemistry in water, or why water? Perhaps there is another suitable solvent. I know it sounds very anthropocentric, but there is so much water in the world, in the universe. There is so much carbon in the universe. Water is it's an excellent solvent, at least for our type of life, and it's an excellent solvent. Period. Water, okay. So why look for other solvents? And then carbon is irreplaceable. To scaffolding large molecules, no way that silicon can do it. It's only carbon. So at least my guess as a biochemist, and I may be mistaken, is that if there is life, it's going to be with the same logic as our life and with the same type of component. The genetic code may be different, the optical isomers may be different, but there will be a code, there will be digital information, and there will be a solvent, and there will be carbon, I think. Okay, thank you very much for your attention.